Good afternoon, everyone. Thank you for joining me for this video. I am Mr. Ish. Today we are going to break away from the topic in that I'm coming back to the concept of vectors. When I presented the 3 videos on vectors, I had stated that that last review video would be the end of it, but then I came to thinking that I never talked about displacement. Displacement is a very important topic, especially when it comes to vectors, and it is also a concept that very well bridges concepts of vectors with regards to math and physics. Displacement is a concept that you do not want to confuse with distance. Take, for example, a quarter-mile track, like a running track. If you run around this a single lap, in terms of distance, and it's a quarter-mile track. Well, let's just say, for discussion's sake, not a single lap, let's say if you do 4 laps of this quarter-mile track, you've done a total distance of 1 mile, of course, because 1 over 4 quarter miles times 4 laps is 1 mile. But now what exactly is displacement? Displacement is basically the final position of a body that had been moving with regards to where it was and where it is. With regards to this track, if you do 4 miles or 1 mile or however many miles or however many laps, if you've done 4 laps of this track, your displacement is actually going to be 0. Even though you've run a distance of 1 mile, your displacement is going to be 0. And that's the conundrum about this. While you may have run a certain distance or a significant distance, your displacement is 0 because where you started, your initial position and where you ended, your final position, happen to be on top of each other. Think of it in this way: if you start over here on this starting line over here and you end exactly over here, your displacement is 0 miles. But how do we talk about displacement in terms of vectors? Well, that is going to be the subject matter of this video. But before we actually start talking about displacement, there's one important thing we need to revise very quickly. It is about the horizontal and the vertical components of vectors, because those calculations of horizontal and vertical components will come very much into play as we calculate displacement. But before we talk about horizontal and vertical displacement, it is important to detail 2 important terms. One is collinear and the other is non-collinear. Non-collinear. Either single L or double L. I would say it's a double L. Collinear are basically the 2 lines which are on top of each other, or basically 2 lines which are parallel to one another. You could literally put one line on top of the other. They would be collinear. It's got nothing to do with the dimension of the lines. We're talking about here in terms of direction. Remember, vectors have 2 qualities to them. There's a direction component, there's a magnitude component. When I'm talking about collinear lines and non-collinear lines, here I'm stressing more on the aspect of direction. Two lines are collinear if they are parallel to one another. If they can be in opposite directions, one can be long, one can be short. They can be in any direction, but so long as the 2 lines are parallel to one another, however much their magnitude may differ, but their direction, relative direction, is at least collinear to one another. It could be in opposite direction or it can very well be in the same direction. These are collinear lines. Non-collinear lines would be 2 lines which do not have the same direction. An example would look graphically like this. See, they're non-collinear. Non-collinear lines cannot be superimposed on top of each other, whereas collinear lines can be placed on top of each other. So before we talk about those horizontal and vertical components of vectors as that review, and we actually get into the concept of displacement, let me present a few quick examples regarding collinear and non-collinear lines as they pertain specifically to displacement. So let's take a look at collinear lines. If you have collinear lines, if supposedly you walk from distance A, you're walking, let's say, 5 miles eastward, then again you walk from that resting point additional 2 miles to point B. These are collinear lines. You don't have to worry about calculating horizontal and vertical components of vectors over here to determine your displacement, because your displacement is basically just 5 plus 2. Your displacement is 7. There's no need to break down any of these vectors into horizontal and vertical components, because you could superimpose one line on top of the other. That is, the entire magnitude of that vector was within a specific direction. You could not break it down into multi-dimensional aspects. The entire direction is in one component. There is no vertical or horizontal component. It is either all vertical or it is all horizontal. There's not a mix of the two. Look at this other example. If supposedly you walk from point A, you walk 10 miles in one direction to point B, but then you walk backwards in the same direction, let's say 7 miles. Now you know your net displacement is 3, because you still have collinear lines over here. Even though the direction is opposite to one another, there's still lines you could superimpose. You could take this arrow and superimpose it with the exact arrow on the other side. The only thing you worry about is the difference in between here, and you do have a displacement. The displacement here is 3. Displacement here was 7. Likewise, you can also use vertical lines to calculate collinear displacement using vectors. Again, these all involve a simple need actually, that you do not have to determine vertical and horizontal components of these vectors. You just look at exactly what is and you make your calculation from just that. Look over here. Imagine if you walk from point A in a southwardly direction for 11 miles and you walk in addition, let's say 5 more miles to point B. Now you know your total displacement is 16 because you have collinear lines. You can just add them up. There's no need to determine horizontal components. Horizontal components of all of these two vectors would be zeros. Look at this other example. If you walk in this direction 20, but you walk back 20 over here, these are again collinear lines from A to B and then back to A, 20, but they're in opposite directions, so here your displacement is 0. So that's the beauty of collinear lines. When you're doing vectors involving collinear lines, you just have to do the simple addition or subtraction and that's it. There's no need to start bringing trigonometric functions to determine horizontal and vertical components. You can also have collinear lines in other directions too, but so long as the various lines are superimposable. Look over here at this example. If you walk at a 45-degree angle with reference to the horizontal, you walk to point B for 10 miles. And then you walk again in the same direction, 45 degrees in that same direction, you walk another 5 miles to point C. Here your total displacement is still 10 plus 5, 15. Because these again here are collinear lines. Even though you have a non-horizontal, non-vertical line, you have collinearity over here because you could superimpose these two lines. Even if supposedly you walked backwards over here, let's say you walk back a distance of 12 miles. Now you know your new displacement is 10 plus 5 is 15 minus 12. Here your displacement is 3. All of these three lines are superimposable. So don't just think about collinearity only in terms of horizontal and vertical lines. You're looking at any kind of line or any sets of lines that are collinear to one another. That is, you can put one line on top of the other, even if their direction is exactly opposite. All of these lines have either the same direction or they have exactly opposite. There's no degree in between. And I want to do just a quick example here just to show how we calculate horizontal and vertical components of vectors. Then we'll look at non-collinear examples of displacement. So as a quick reference review example, here is a technique for determining horizontal and vertical components of vectors, and I've demonstrated a similar technique in the video part 2 on vector algebra. If you're pulling a weight and you're pulling it with a string, and let's say the tension in this string is 103 newtons, the force you are requiring to make this object move is 103 newtons, and with reference to the horizontal surface that this weight rests on, you're pulling that string at an angle of 25 degrees. Your goal over here is only to determine the horizontal and vertical components of this vector. This vector has a certain magnitude, 103, and it has a certain direction, 25. And we have to just break it down into its two component vectors, the horizontal and the vertical. The easiest way to do that is to extend this out, make a right triangle, and understand that we have to use simple trigonometry to calculate the horizontal and vertical components. My vertical component is this V, this y-axis line, and my horizontal component is this H, the x-axis line. To determine the vertical component is not hard. You have to think back to how you can relate this angle with this side dimension and the opposite. You know you're going to use a sine formula over here. Check this out. You'll do sine 25 degrees is equal to V over 103 newtons. And the V, the vertical component of this vector or this force would be 25 sine, and you multiply that by 103 and we'll get 43.5 newtons. we can just round that up just for simplicity's sake, 44 newtons. So the vertical dimension of this vector is 44 newtons. To determine the horizontal is exactly the same, except you're looking at now the adjacent and the opposite. So you know you have to involve the cosine function. Cosine 25 degrees is equal to h over 103 newtons, and you solve exactly in a similar manner. Cross multiply and solve for h. 25 cosine times 103 is equal to 93.3. Let's round it down to 93 newtons. So you know the horizontal component of this 103 is h, which is 93 newtons, and the vertical component v is 44 newtons. You can't just add 93 and 44 and say they should add up to 103. It doesn't work that way. We've just broken down a vector into its two components, and those components don't necessarily add up to their original. Okay, they don't add up to that original, so keep that in mind. It doesn't work that way. Now, one thing you should keep in mind is this. If you think back to one of the formulas I presented in my video, actually which I repeatedly presented, was the one on magnitude. If this is your magnitude 103 newtons and you've broken down into its two component parts, you can technically look at it as this way. If this vector, let's call this vector n, you can simplify it or demonstrate it as this, n1 and n2, right? n1 comma n2, these are its two component vectors. We've basically broken down 103 into 44 and 93. Now I said very early, a few minutes ago, that you can't just simply add these two numbers and expect they'll equal to 103, but you do know what the formula for magnitude is. Magnitude of any vector is always equal to the square root of the sum of the individual components squared. You're adding them up, right? Now if you do the square of this and you do the square of this, you add them up and you take the square root, you should get 103. So that's how the components of vectors relate to the original value. They don't relate simply by just adding the two and you get the original. They relate in this form. You take the individual component values, you square them out, you add them up, meaning in the sum total, then you take the square root, then you'll get the 103. If I did 44 square, and then I did add that to 93 square, and I square root that, I get 102.88, which is 103, close enough. So that's how components relate to the original magnitude, by this formula over here. So without digressing further, let's actually talk about non-collinearity in the rest of this video. So again, remember, displacement is just basically the difference between the final resting position of an object and where it was initially. If that final resting object is right on top of where it originally was, then there is no net displacement, meaning the displacement is zero, even if supposedly the distance may have been a significant amount. For instance, if you carried an object around a 1 mile track, you've done a distance of 1 mile, but your displacement, you take it back to the original point, your displacement is zero. So keep that in mind. Displacement is different vastly from distance. Here is an example of non-collinearity, where you have some lines which might be collinear, that is, they're superimposable, but there's some lines that are not. If supposedly your starting point is here and you walk 3.5 miles north, then you walk 4.2 miles directly east, then you walk 1.4 miles directly south. And the question is this: what is your displacement? If you don't want to use a traditional approach where you're using the protractor and rulers and doing exactly everything accurate, that is one way of doing it. But if you don't want to do that and you want to rely on calculator, that's fine. But then you have to understand that you have to calculate the resultant. And remember, we're going to be calculating the resultant. The resultant will be the direction and the magnitude that will give you your displacement. Your resultant will of course be from your starting point right here to my ending point right over here. So you just draw an arrow over here. Your goal is basically to determine the displacement. By determining the resultant, the components of this resultant, we will determine the displacement. So how you proceed is this. You basically have to simplify your diagram or your scenario as much as possible as you can by determining what items within the example are collinear. For instance, look over here. We have two collinear lines. We have this upward northerly direction line and we have this southerly direction line. These are collinear, even though they may not be in the same direction or the same magnitude. They're collinear because you can superimpose them. And you can simplify your process by this. If you are going 3.5 miles north directly and you're coming down 1.4 directly, it doesn't matter in what sequence you're doing this, you can convert this into a net because these are collinear lines. They're superimposable. 3.5 miles up and 1.4 miles down south, there's no need to determine horizontal and vertical components. You just do 3.5 and you minus it from 1.4 and you get 2.1, which means you have a net displacement of 2.1 miles in an upward direction. But we still have to deal with this 4.2. But now the whole process has become easy because we can re-diagram all of this into a simpler version, and this is how we're gonna do it. Look over this 2.1. Let's create a new diagram over here. We don't have to do anything to scale. We basically have a 2.1 displacement upwards and we have a 4.2 displacement here, and all we have to do now is calculate this resultant. And what we end up here is a right triangle, and we have everything we need to determine this dimension using simple trigonometry. We have two sides, the length and the base, and we have to determine the hypotenuse. A square plus b square is equal to c square. And we can also use trigonometric ratios or trigonometric angles, the function definitions, to determine this angle right over here. Let's do a square plus b square and we'll calculate that last side. Look over here. 2.1 square plus 4.2 square, you get 22.05 square root that, you get 4.695. This side over here, the magnitude resultant is 4.695 miles. So you basically have a net displacement of 4.695 miles. Let's do m for miles. Now all we have to do is calculate this angle over here. We can calculate the angle of this x by using cosine. Watch over here. Cosine x is equal to 2.1 adjacent over hypotenuse, 4.695, and x will be equal to the arc cosine or the inverse cosine of that. So do 2.1 divided by 4.695, inverse cosine it, and you get 63.43 degrees. 63.43. So here's our angle, 63.43 degrees. You could have done everything with the exact use of vectors by doing proper ruler and protractor usage, angles and everything, and you could have easily calculated this to be 4.695 with an angle of 63.43, but the calculator makes it so much easier. So now look at this question over here. This question will involve non-collinear vectors to determine the final displacement of this car. A car travels 34 miles in this direction, north 30 degrees west, then it stops, and then it does an additional 58 miles north 40 degrees east. Of course, all of this is hypothetical. You can never travel in a straight direction infinitely. There are always obstacles along the way, but this is just for the process of learning. The process for tackling these type of questions is to draw them out. You always draw them out in sequence as how the writing is. This right here represents sequence number 1, this represents sequence number 2. So let's have a starting point over here. And it goes 34 miles north, 30 degrees west. If this is north, right, it's going 30 degrees west. Alright, it's going 30 degrees west of the north line, and it's going at a distance of 34 miles. Alright, now it makes another stop. So here, let's draw another axis over here. From here, it does 40 degrees east of the north line, 40 degrees east of the north line, and this time it travels 58 miles. And it stops right over here. So you're basically asked to determine the displacement. The displacement is basically just a fancy term for the resultant. You're basically tasked to determine what's the magnitude and the direction of this resultant, which will represent your displacement. You could technically use a ruler and a protractor, as I showed you in that traditional approach of doing vectors, and you can do this without a calculator. You'd have to draw this exactly to scale with the proper angle. You'd have to draw this exactly to scale, length and everything to the proper scale and proper angle, and just determine the length and direction of this, and you'll get your answer. But we want to do this using components of vectors, and we want to do this using the calculator. So to actually solve this problem, we have to look at both of these components. We're going to call these A and B. We have to look A and B in their proper sequence, and we're going to draw them out separately. Let's draw the A component out. You have A component looking something like this. If you were to extend this line over here all the way up to this horizontal over here, you get basically a right triangle. And you know this angle over here is 30 degrees because you were traveling 30 degrees west of north. If this is my north line, we would just shift it 30 degrees in this direction, and we have a right triangle over here. We have a 34 over here, which represents the hypotenuse, and we have one side over here which represents, let's call this horizontal 1, and we have one side over here represents vertical 1. We have to determine horizontal 1 and vertical 1 using the trigonometric ratios for this first event of the journey, then we'll do the exact same for the next event of the journey, then we'll go from there. We're determining the horizontal and vertical components. To determine the horizontal component over here, now you have to use actually the sine formula, because the horizontal component is actually opposite to your angle. So to determine the horizontal one, we are doing this. We're doing sine 30 is equal to h1 over 34, and just solve for h1. Sine 30 is 0.5 times 34 is 17. So our horizontal component is basically 17 miles, because we're talking here about miles. Let's do the v component. The v component here is actually going to involve your cosine value, because the v component here actually happens to be adjacent to your angle. So you'll do cosine 30 is equal to v1 over 34, and you solve for v1. v1 will be 30 cosine times 34. I get 29.4. Bring in decimals here, 29.4. Now we have to do the horizontal and vertical components for the second component of this journey. Look at the second component of the journey. You can extend this line up over here, and then extend it across, and we've gotten a right triangle. And let me show you how that looked. We had an angulation over here of 40 degrees. See, we're 40 degrees east of the north line. If this was my north line, we traveled 40 degrees east of this north line in this direction. Here's my vertical component. Let's call this vertical component 2, and let's call this horizontal component 1. And we know we have a distance here 58, which is your hypotenuse. Now again, you have to use trigonometry to calculate v2 and h2. I should have put an h2 over here. Let's do h2. Now with reference to this angle, h2 again happens to be an opposite, so we have to use sine over here. Now watch, sine 40 is equal to h2 over 58. And you know h2 over here is going to be 40 sine times 58. So let's bring out that calculator and do it. 40 sine times 58. I get 37.3. 37.3. Now let's do the v2 component. See, we're doing horizontal and vertical components. The v2 is actually adjacent to your angle, so you're going to use cosine. Cosine 40 is equal to v2 over 58. So what's the value of v2? Just do your simple trigonometry. 40 cosine times 58, I get 44.4. 44.4. This is my v2 component. 44.4. Now look over here. By breaking these vectors into their horizontal and vertical component, or let me say this, by breaking these non-collinear vectors into their horizontal and vertical component, we've basically developed two pairs of collinear sides, or two pairs of collinear vectors. The h1 and h2 are collinear because if they're horizontal, they're of course going to be superimposable. The v1 and v2 are now collinear because if they're vertical, of course you can superimpose them on top of each other. Now you just have to determine, is this collinearity or this superimposability in the same direction? If they are, you'll just add them up. If they're in opposite direction, then of course you have to minus things. Look over here. You were going up in this direction in terms of this vector, then you were going in this direction. Your v1 was going up, let's put it here, this was your v1 and this was your h1. Now look over here, my v2 was collinear to v1 in the same direction, but my h2, it was collinear to h1 but in the opposite direction. So the both v vectors, the v1, v2 must be added, but the h1 and h2 must be subtracted from one another because they're in the opposite direction. You went up this way, your vertical component this way and this way. And you can think about it like this, you went in this direction, then you went in this direction. So in terms of the horizontal components were superimposable but in opposite directions. The vertical components are superimposable but in the same direction. So now let's get our net horizontal component, and let's get our net vertical component, because these will be the items that will help you obtain your dimensions of your resultant. Net horizontal components are supposedly to minus from one another. You'll do 37.3 minus 17. You'll do 37.3 minus 17, you get 20.3. Because the two horizontal components were superimposable but in different directions, so you minus them. Take the large value and you minus it from the small value. The two vertical components are superimposable but in the same direction, you add them up. 44.4 plus 29.4. 44.4 plus 29.4. And that gives you 73.8. 73.8. And think back to what I just mentioned at the very beginning. You can't just add these and they give you your resultant magnitude, but you know there's a specific relationship between this and that magnitude, and the magnitude relationship was this. The component for any vector magnitude was equal to the sum of the squares of the individual components and their square root. Do these same things over here. You'll do over here for your resultant, you'll do the sum of the squares and the square root of the individual components. 20.3 square plus 73.8 square, and you'll square root it. So let's do 20.3 square plus 73.8 square, and you square root it. I get a resultant here of 76.54. Let's write over here. My resultant over here is 76.54, or let's just keep it 5 miles. So with us having solved for this magnitude over here of your resultant of 76.5, or you can round it up to 77, now our task remains of determining the actual angle. And the formula for angle is always arctan of the y value over the x value. Now your trick over here is, or let's just say your challenge here is, which of these represents your y value, which of these represents your x value, which represents the vertical component, which represents the horizontal component. That's what you have to determine. But you have to do that in terms of relation to this angle which is down here. If you were to draw this out, of course this right here represents your height of this vector of your resultant. If you look at your resultant, this is my resultant, you can draw a set of line over here, and you can carry it down from over here on the top and bring it down and draw your right triangle. Here would be my horizontal component, here would be my vertical component. But you have to do this in relation to your angle. Your angle would of course be over here, right here. Your angle is basically this angle right over here, which is of course the same as this angle over here, that angle over here. With regards to this angle, you have a height over here of 73.8 and you have 20.3 across, a horizontal component of 20.3 across and height of 73.8. With regards to this angle over here, your opposite is 20.3 horizontal component and your adjacent is 73.8. So basically what you're turning out having is 20.3 as your opposite component divided by your adjacent component 73.8. Remember, one of the definitions of tan is opposite over adjacent. Well, your opposite side with reference to the angle, whichever side you look up, whether you look upwards or you look downwards from this angle, is always 20.3 divided by 73.8. So you do 20.3 divided by 73.8, you inverse tan that, and you get an angle of 15.37 degrees. I'm going to round that to 15 degrees. So basically we've gotten our 15 degrees over here. Let's just write our final displacement. Our displacement is basically going to be 76.5 miles in a direction of north 15 degrees east. If this is my north line over here, I only tilted 15 degrees in this direction. My resultant only tilted 15 degrees here. And that's this question done. But you can see when you have non-collinear vectors, the process becomes much more elaborate. Versus when you have collinear vectors, we can simply add them, subtract them based on whether they're in the same direction or opposite direction. So let's look at this question. You have a car which drives 10 miles directly north 10 degrees east. It makes a little stop. Then it does 100 miles at south 45 degrees east from that initial stop. You have to determine the displacement over here. And when I'm saying displacement, you have to determine the resultant. You have to determine the magnitude, which is representing the distance traveled, or your displacement here in this case, and you have to determine the direction of that displacement. Like with regards to where your car started, where has it ended up? That is your displacement. So to actually determine the displacement of this car, we have to draw it out to help us guide our way through. If this is my north line over here, the north direction, I know I drove 10 degrees east of this, 10 degrees east of this, 10 degrees in an eastwardly direction, and I drove for a distance of 10 miles. From this stop over here, let's draw a little axis. From this stop at an axis of 45 south, 45 degrees east, 45 degrees east. Let's say 45 over here. You can even say from this southwardly line, we went 45 degrees in that direction. It's still the same, 45 degrees for a distance of 100 miles. We have to determine our final resting point in terms of displacement, which will be over here. What is the dimension and what is the direction of this displacement, of this resulting vector? That's what we have to determine. So there's no collinear lines over here, but if we were to break these down into their horizontal and vertical components, we can develop collinearity of those horizontal and vertical components. To proceed, let's look at this first triangle over here. The first triangle looks something like this, and you don't have to do drawing. I only do the drawing because it helps me visualize the problem. I have a 10 degree over here. I'm looking at this part right over here. This initial triangle, which represents the initial sequence. And you can draw a right triangle, and we know we drove 10 degrees east of the north line, and we did a distance of 10. And we know we have a vertical 1 component here and a horizontal 1 component, and we can use trigonometry to calculate them out. Let's do vertical 1. Vertical 1 here happens to be adjacent, so for vertical 1 you're going to do cosine 10 degrees is equal to V1 over 10. Let's look at H1. H1 is opposite to your 10 degrees tangent. Look at H1. H1 you'll use sine 10 degrees is equal to H1 over 10. Let's calculate these values out. V1 will be 10 cosine times 10. I get a 9.8. We're only going to take things to one decimal place. 9.8. That's my V1 component. 9.8. Let's look at the horizontal 1 component. Sine of 10 degrees times 10, I get a 1.7. I'm only do one decimal place, 1.7. Now we should look at our other triangle. We have to draw this out. Extend this southerly line all the way down and extend it across. And that gives us a representation of a triangle. We know we're going 45 degrees. See, here's my south line. We're going 45 degrees, and then we went a distance of 100 miles. We have to determine the V1 component, and we have to determine the, let's say, V2 component and the H2 component, because this is our second sequence. We have to determine the second set of sequences over here, components. Let's do V2. What will we use for V2? Again, it's adjacent to your angle, so we'll use cosine. Cosine 45 is equal to V2 over 100. What about H2? It's opposite, so you're going to be using sine. Sine 45 is equal to H2 over 100. Now let's solve for V2 and H2 and put their values down. They'll be the same because cosine 45 is equal to sine 45. 45 sine times 100. I'm getting a 70.7. This is a 70.7 and this right here is a 70.7. You'll get the same exact values because sine and cosine of 45 are the exact same values. Now look over here. We got collinear vectors here. V1 and V2 are collinear. H1 and H2 are collinear. You just have to determine, are these collinear vectors gonna add with each other, or are they gonna subtract with each other? Well, let's look. For the V1 we're going directly up. For the vertical 1 component we're going up. Well, for the vertical 2 component we're going down. So we know the V1 and V2 have to minus from each other. Now let's look at the H1 and H2. For the H1 component we're going in this direction, towards the easterly direction, but for the H2 component we are also going again in an easterly direction, so we have to add those two components. So now that we've gotten the components V1, H1 and V2 and H2, we have to determine how they're going to combine together to give you your net H and your net vertical components. You have to look at their directions. So the two vertical components are superimposable collinear lines but opposite to one another. The two horizontal components are superimposable and collinear lines but in the same direction, so you can add them up. So let's look at the H components, the horizontal component. You'll add 1.7 to 70.7. 1.7 plus 70.7 and your net horizontal is 72.4. 72.4 miles, the horizontal component. Now let's look at your vertical components. 9.8 up and 70.7 down. So you just minus them. Take the big number and minus it from the small number. 70.7 minus 9.8. 70.7 minus 9.8 and you get 60.9. 60.9. Again, to determine the resultant, you can just use a simple formula of the sum of these two individual numbers and square them out. You can do 72.4 square plus 60.9 square and you will get your resultant. What will your resultant be? Let's do it out. Let's calculate it. Your resultant will be 94.6. What about your angle? We have to get our angle. Well, to get our angle, we have to actually determine the angulation of this. We have to determine this angle. Again, of course, from the horizontal. If our starting point is here and our ending point is here, everything is always with reference to horizontal. We have to determine this angle. We know we've done a displacement here of 94.6, but what exactly is our angle? To determine the angle, take this triangle over here and extend it across over here and bring it down over here. So you can start determining with reference to this, what will be your y value, what will be your x value. We know our net horizontal was 72.4. We know our net vertical was 60.9. With reference to this angle, my opposite is 60.9. So theta is equal to arctan 60.9 divided by the adjacent. Because remember, tangent is always opposite divided by adjacent. So 60.9 divided by 72.4. 60.9 divided by 72.4, inverse tan that, I get a 40 degrees. So you can say that in this type of format, you can say it's south 50 degrees east. Because if you're 40 degrees from the horizontal, then from the southerly line you must be 50 degrees. That'll give you a 40 over there. So our resultant or displacement is 94.6 miles at a direction of south 50 degrees east, or you can say 40 degrees from the horizontal line. So this question has been done, but you can see it's a little complicated because we don't start with collinear vectors. We have to break them down into their horizontal and vertical components. From there, you can actually start developing that collinearity and doing the superimposability, and then doing the simple addition, and then simple addition, subtraction, and then determining the magnitude of the direction. I should present one more such example, and then we should be wrapping it up with this video. So here's a last example of ours, a displacement question. We are in a vehicle which travels 15 miles south 60 degrees west. It takes a pause, then it does an additional 35 miles north 80 degrees west, and we know the initial point and the final point are not the same, so there will be displacement occurring. The best way to proceed through this is to split this up into two parts as shown and to draw it out. Let's do our starting point. We start our point by drawing like a compass axis, north, south, east and west. This is my south direction. South line. I'm doing 60 degrees west of that. I'm doing 60 degrees west of that, and I end up going a distance of 15 miles. And we come to a stop over here. And then from here we do from north 80 degrees west. Let's do another compass direction here, and here's my north line. We do 80 degrees west of this, 80 degrees west. 80 degrees west of this northerly line, and we do a task of 35 miles. We're not drawing here things to scale because we're not using the protractor method. And we have to determine this resultant right here, the magnitude and the direction. The best way to go from here to the next step is to split this up into individual triangles. You can actually create triangles over here individually. Look at the first scenario. We know we are 30 degrees over here because from here we are 60 degrees in this direction. If you create the horizontal across, you've gotten your 30 degrees. And we know we've done a distance over here of 15. You can close this up, make a right triangle, and you've gotten your horizontal 1 and your vertical 1 components. And we can do exactly what we need to do using basic trigonometry. Let's do horizontal 1 component. Here the horizontal component is adjacent to your angle, so we'll be using the cosine formula. You'll do cosine 30 is equal to h1 over 15, which is your distance traveled. Your v1 of course will be sine 30 is equal to v1 over 15. Just calculate these h1 and v1s. Remember, we're converting non-collinear vectors into collinear vectors, which will be horizontal and vertical components, which we can add or minus from your next set of horizontal and vertical components. So h1 will be 30 cosine times 15, and you get 12.99. I'm actually rounding that up to 13 because 12.99 is very close to 13. Let's do sine. Well, sine 30 is 0.5. 0.5 times 15 is 7.5. That's easy. Now let's draw our second set of triangle, which represents the second aspect over here. We went north 80 degrees. So let's draw a line over here, and we went 80 degrees in this direction. And we went for a distance of 35 miles. Let's close this off over here and draw up our right triangle. We have exactly what we need over here. We have a 35 which represents our hypotenuse. We have 80 degrees which represents one of the angles in your triangle. We have a V1, actually V2. I keep making 1 and 2 mistake. And H2. Let's do V2 and H2. Now here the vertical is adjacent to your angle, so you have to use the cosine formula here for the vertical. Here we're using the sine for V1, but here we're using the cosine. So the cosine of 80 is equal to V2 over 35. And what about H2? It's opposite to your angle, so you're using the sine over here. Sine of 80 is equal to H2 over 35. Calculate these out. What do we get? V2 will be 80 cosine times 35. I get 6.077. Let's make this 6.1. That's your vertical component for the second set of vectors. Let's do H2. 80 sine times 35. I get 34.46. I'll make that 34.5. 34.5. Now all we have to do to determine is the superimposability of these horizontal and vertical components. H1 was in this direction. H1 was in this direction because we were in both instances going in a westerly direction, and H2 again is in this direction. So the both H1 vectors will just add. There will be nothing minusing from them. V1 of course is going in a downwardly direction. Remember, we were going originally downward, so the vertical one component is downward. But then we're going, you see, here the southerly direction, so the vertical component is south. Here's the northerly direction, so the vertical component for V2 is upward. Here the vertical component is upward. So now we know the horizontal components are going to add, but the vertical components will minus. So let's determine the net. The net horizontal is basically going to be the sum of the two horizontals, 13 and 34.6. 13 plus 34.5 actually, we get 47.5. And now the net vertical components, they're going to minus from each other. The big number minus the small number. 7.5 minus 6.1. 7.5 minus 6.1, I get 1.4. 1.4. So what's my resultant magnitude? It's going to be the square root of the sum squares of these numbers. 47.5 square plus 1.4 square. And what do we get? I get 47.5. It's so close that it's easy just to say 47.5. So my total displacement is 47.5 miles. This right here is going to be 47.5 miles. But we have to determine the direction now. The direction is always equal to the opposite divided by the adjacent. Now, because we're going to use the inverse tan, we have to determine which of these two values represents the adjacent, which of these represents the opposite. And you have to do that with reference to your angle from the start. If you draw a clear horizontal going across over here, and you make a right triangle over here, you essentially have something which looks like this. A very long triangle upside down. Here's my angle over here, my reference angle. Here's my 90-degree line, and my resultant magnitude here is 47.5. And I have a net vertical here, I have a net horizontal here. So with reference to the angle, the vertical is the y component and the horizontal is the x component. So it's going to be inverse tan, the vertical component net 1.4 divided by the horizontal component net 47.5. If you cannot determine which one is your y, which one is your x based on your angle, then you will be doomed in terms of presenting a right answer. 1.4 divided by 47.5 inverse tan, I get a 1.688. 1.688, let's round that to 1.7 degrees. We have a very small net direction, 1.7 degrees. But what does that 1.7 degrees mean in terms of this format? We're going, let's say 1.7 degrees, we're going, let's draw a north line, south line, east line. We're going 1.7 degrees, you can say, let's do minuses from 90, you get 88.3. So our resultant here is going to be basically south 88.3 degrees west. Because south 88.3 degrees west is equal to 1.7 degrees from the horizontal, from that horizontal, the 180 degree line. This right here, 1.8 degrees right here, or 1.7 degrees, which is 88.3 degrees south, 88.3 degrees west. Let's write our resultant right here. It's 47.5 miles. The angle is 1.7 degrees from 180 degree line, or you can say south 88.3 degrees in a westerly direction. That's your final displacement components in terms of the direction, in terms of the magnitude. This question can get a little messy, but it's not hard. It requires a lot of process and procedure to it. You're basically converting non-collinear lines into their collinear components, because then you can determine the superimposability and just do the simple adding and subtracting. The challenge then is, of course, to determine, are the horizontal components in the same direction where you just add them, or they're opposing each other where you minus them? Are the vertical components in the same direction where you will just simply add them, or are they in opposing direction, superimposable, but in opposite directions where you'll minus them? And you always have to use these formats over here to give you a direction or a hint towards a direction. You're in these questions, you're both always going in a westerly direction, so you knew your horizontal components will add. But here, in terms of the vertical components, remember north and south are vertical, east and west are horizontal. In terms of vertical components, you're going initially south and you're going north. So that gave you the idea that the vertical components would subtract from each other. I admit that this video has been a little messy in terms of the writing and a lot of displaying on the board, but I hope you were able to pick out the pieces of information that I presented. The ability to visualize these triangles is not always easy. It takes practice. Maybe if you all want, I can present another video on the same topic and go through more examples. But I hope you enjoyed this video. You have the benefit of looking at these through slow motion or in the form of stills, and just to pick out all the pieces of information that you need. Please like, subscribe, and share. Thank you for watching, and have a nice day.